Hello guys, so we are going to continue the discussion with respect to natural language processing for machine learning. In this video, we are going to discuss about word embeddings. And this was probably the topic that I should have covered long back, but I'm deliberately keeping this particular topic at this point of time. Why? Because we have discussed so many topics wherein we focused on converting word into vectors. So now you'll be getting a very clear idea about what exactly word embeddings is. And here I've given you a Wikipedia definition. So this is a very simple Wikipedia definition. I have taken it from Wikipedia. So the entire credit goes to Wikipedia over here. So over here you can see the definition that in natural language processing, word embedding is a term used for representation of the words, right? For text analysis, typically in the form of real valued vectors that encodes the meaning of the word such that the word are closer in the vector space are expected to be similar in the meaning. So let's say that I have two words, king and queen, okay? Or forget about king and queen. Let's say that I have two words and the two word is like happy and excited, right? Let's say I have this two specific word. Now, when I have this two specific word, with the help of word embedding techniques, what we do is that we convert this particular word into vectors. And let's say if I try to plot this vectors in a two-dimensional graph, okay? And if I really want to convert this into two-dimensional graph, we have techniques like PCA or other techniques, which is an unsupervised technique to do dimensionality reduction. So once I probably plot this, let's say happy and excited are coming near to each other. Based on this particular vectors, it basically indicates both are similar word. Okay, let's say that I have one more word like angry. Now in this case, with the help of word embeddings, if I'm trying to convert this into vectors, the tentative thing is that obviously happy is the opposite to angry. So angry will be somewhere here. If I probably try to plot this particular vectors over here. Why? Why it is coming so far? Because it is an opposite word. So the distance between this word will be quite high. Whereas the distance between this particular word will be quite less. So this indicates that both the words are similar, whereas both words are opposite to each other, right? And this is all possible because of efficient conversion of the word into vectors, right? And how we are doing this? Again, with the help of word embeddings. But the techniques we have learned till now, it is something like one-hot encoded we have learned, about bag of words we have learned, TF-IDF we have learned. And all these techniques are a part of word embeddings. So if I properly, clearly show you the division, in the first step, if I have the word embedding techniques, so let me just again go ahead and write it. Word embedding techniques are specifically of two types. So this is my first type and this is my second type. The first type is based on count or frequency. Count or frequency. And the second type is based on deep learning trained models. Please hear to this very properly, because this deep learning trained models will give you very good accuracies. Okay. Now in count or frequency, we have learned about three different types. One is one-hot encoded. Second one is something called as bag of words. And the third one is something called as TF-IDF, right? So all these techniques we have learned, right? And we know the advantages and disadvantages. But here we are focusing more on count of frequency, right? But the major one, which is having a better accuracy, which is actually, and all these techniques at the end of the day is also converting words into vectors, or it is converting sentence into vectors, right? Sentence into vectors. But we have seen a lot of advantages and disadvantages. Maximum number of disadvantages are there with respect to all these techniques. And all disadvantages are getting solved by this deep learning trained model. And the trained model is nothing but, which is basically called as Word2vec. It's not like we cannot create it from scratch. We can definitely create it from scratch. But again, you require a huge amount of data. And what we are going to do in that, first of all, we are going to understand in the upcoming videos what is exactly Word2vec and how it is basically converting a word into vectors and how it is solving all the disadvantaged things that were there in this particular technique. Everything we are going to discuss. But just understand that what is Word2vec? It is a word embedding technique which will efficiently convert a word into a vectors, which will be making sure that both this property, It is expected to have similar in meaning whenever it is converting into a vector space. Along with that, it will also give you a very good representation of the words, right? Sparsity will not be there and all. There are many points which I'm going to discuss in the upcoming videos with respect to Word2vec. Now, Word2vec are of two types. One is because the entire deep learning architecture is built on two different types. One is, we basically say CBOW. CBOW is nothing but continuous bag of words. Super important, continuous bag of words. And we are also going to see that how the models get trained. But for this, you really need to have a prerequisite knowledge of how an ANN works. What is loss function, what is optimizers and all, right? The second technique is something called as skipgram. Again, this is a different technique. And again, it is a part of Word2vec itself. It is a different type of Word2vec. At the end of the day, we can either use CBOW or skipgram to get an efficient conversion of word to vectors, right? And this is what we are going to see. We are also going to see some pre-trained models of Word2vec, probably created by Google, and it is somewhere around 1.5 GB big model size. We'll try to download it. We'll try to see, we'll try to execute it. But in the upcoming videos, what we are going to see is that how Word2vec word embedding works, right? And how it is making sure that all these disadvantages that are present in these techniques is getting removed, right? So this is what we are going to discuss, but I hope you got an idea. At the end of the day, whatever techniques we have discussed till now in converting word into vectors, it falls under word embeddings, right? So yes, this was it from my side. I will see you all in the next video. And in the next video, I'm going to discuss about Word2vec. Hello guys, so we are going to continue the discussion with respect to natural language processing. In this video, we are going to cover Word2vec. We have already seen what exactly Word2vec is. It is a deep learning trained model. And again, it is a kind of a word embedding techniques wherein the focus is to convert word into vectors, making sure that the meaning of different words are actually maintained. Like if there are similar words, we'll be getting vectors that are very near to each other if we probably find out the difference. And we'll also be able to see that which all words are completely opposite based on these vectors. Okay. So let's discuss about Word2vec, and I will give you an idea about like what exactly is Word2vec and how the words is getting converted into a vectors. In the upcoming videos, I will try to show you that how Word2vec models are basically prepared with respect to architecture in the case of deep learning models. And for that, you really need to have knowledge about ANN models, right? If you really need to understand that how we can train Word2vec from scratch. Okay. And yeah, let's go ahead and with the definition, and let's see that what all problems it actually fixes. So over here, Word2vec is a technique for natural language processing published in 2013, and it was published by Google, an amazing company. Already you know that, and they have done some tons of work with respect to NLP. They're doing a lot of research. The Word2vec algorithm uses a neural network model. We'll be discussing about this, how we'll be using it, how it uses a neural network to learn word association. Please make sure that you understand these words. To learn word association from a large corpus of text. Once trained, such a model can detect synonym words or suggest additional words for partial sentence. So it will be able to detect synonyms. It will be able to detect opposite words and many more things. As the name implies, Word2vec represents each distinct word with a particular list of number called as vectors. So at the end of the day, we are converting a word into vectors, but this vector will have many things. It will be able to detect synonym words, or it will also be able to suggest additional words for partial sentence. Okay. Now let's understand what exactly this is. Now see guys, in bag of words, TF, IDF, we have already seen, right? Based on the vocabulary size, we'll either get ones or zeros. And in short, we are getting a sparse matrix. In TF, IDF also, we may get decimals like 0.25, 0.6. Then again, zeros are there. In Word2vec, it will be a little bit different. Now let me talk about how it will be different. Let's consider that I have a vocabulary, okay? And I have a vocabulary. Let's say I have my vocabulary. So these are basically this many number of unique words I have in my corpus. Okay. Unique words I have in my corpus. Corpus basically means paragraph. Okay. Now let's say the vocabulary words that I specifically have, like something like boy, girl. Okay. and then we have something like king, queen. And if I probably talk about some more words like apple and mango. Let's say in my vocabulary, I have this many words, okay? Now one very important word I'm going to put up over here, which is called as feature representation. Feature representation. Please listen to me very, very carefully, a very important topic. Now each and every word that are present in the vocabulary will be converted into a feature representation. Now what this exactly means? This basically means that we are going to convert this all words into a vectors based on some features. Now what all features can it be, right? Let me give you a very good example about it, but understand that when we are training a very big Word2vec model, at that time you will not be getting a clear idea about all the features. But here, just to make this intuition, to make you understand the intuition, let's discuss about this feature representation. So in the left hand side, what will happen is that, let's say that I will be having a lot of features like this. So I may be having a feature called as gender. I may be having a feature called as royal. I may be having a feature called as age. I may be having a feature called as food. Like this, I will be having a lot of features. And let's say that the total number of features, are basically 300 dimension. That basically means I will be having one more nth feature over here. And the size of this entire features, like if I probably count all of this, this will be 300 dimensions. Let's consider 300 dimension basically means I will be having this 300 features. Now with respect to all this vocabulary, we are going to represent this word in the form of vector considering this feature representation. So this is my entire feature. Okay. What I'm actually going to do, I'm going to take up all these words that are present in the vocabulary. Based on this particular features, we are going to assign one numerical value. Okay. And understand one thing, this numerical value will be assigned based on the relation of these two words. That is the vocabulary and this feature representation that we have. Here I have given you as an example, but when we are training a very large Word2vec model, we will not be able to see these features entirely, right? If I take an example of Google, they have come up with this amazing Word2vec model, which is basically trained in 3 billion words, I guess, 3 billion words, which is coming from the news feed, right? And that practical example also will try to show you. And at the end of the day, you'll be able to see that each and every word is basically represented by 300 dimension of feature representation. That basically means every word will be having a 300 dimension vectors. Okay. Now this is super important. What kind of values that I can have over here, right? What kind of values I can have over here? Now let's say with respect to boy, which is present in the vocabulary. Okay. And its relationship with respect to gender, let's say that I'm having -1 over here. Let's just consider, okay, -1 over here. Now with respect to girl and gender, the value can be +1 because it is the opposite of boy, right? Opposite with respect to gender, if I say boy is there, opposite of boy is nothing but girl. So -1 and 1, this kind of vectors can come. Now here you can see with respect to the next word. Over here we have boy, we have royal. We obviously know, we cannot say, right? We don't have a sentence that, oh, he's a royal boy. He can be a royal prince or he can be a royal king, right? So there is no proper relationship. So in this particular case, there will be a value like 0.01. I'm just giving you as an example, right? Similarly, we will also be having with respect to boy and age. Let's say that there is not much relation. So I'm just going to put it as 0.03. Okay, very near to 0. Now similarly, I can have all these values over here, and these all values comes through proper trained models like Word2vec, which is trained by deep learning techniques like ANN. Okay, and I'll show you in the next video how those models are basically trained. But just understand over here, each and every vocabulary that we are seeing is represented based on this feature representation. So that basically means for boy, I will be having this vector. So for boy, you can see over here, I will be having this specific vector. Okay. So this all vectors will be here. Okay. Now similarly with respect to girl, now you can see with respect to gender, if boy is having -1, then this will be +1, right? Because it is completely opposite. With respect to royal, again, no relationship. So it will be 0.02. Let's say here I'm going to put 0.02 because age with respect to this also no specific relationship, right? So similarly, I will be having other values like this. Now see, with respect to king, I may have gender like there is a relationship with respect to gender and king. So minus 0.92 will be there. With respect to queen, it can be plus 0.93, you know. So here you can see opposite, right? Opposite over here, right? And similarly, I can have other vectors like over here, royal and king are related, right? So I can have 0.95, okay. And over here, you can see also royal and queen can also be a royal, right? So over here, probably the value can be 0.96, 0.97, very much nearby each other, right? Now understand, because of these vectors, you know, similar words will be very, very close to each other, because if I try to subtract it, I'll just give you an idea about it. So right now with respect to age also, obviously there will be some relationship between age and king, because we say that old king, right, with respect to age. So suppose let's say here I'm having 0.75, here I'm having 0.68. And like this, I will be having multiple vectors like this, right? And we can clearly see, right, over here it is. Now you see, with respect to apple, obviously it will have no relationship with respect to gender. So I can probably write 0.5 or 0.01 something, right? With respect to mango also, it cannot be. So I'll write just 0.23. I'm just saying that, okay, we basically can have some values over here. If it is not having a relation, it will be very much near to 0, like 0.05. Okay, I'm just putting some values. But once we train all these models, right, we will be getting this value. Here I'm giving you a crux idea about like how each and every vectors may look like. Okay. Now over here, with respect to apple and royal, also I'll not be having much relationship. So let's say I'm putting minus 0.202. This will be plus 0.02. With respect to age and apple, this may have a very good relationship, right? Because let's say if the apple is kept for 10 days outside, you know, it may rotten up, right? It may not have that nutritional value. So this, with respect to age, it may have a direct relationship. Mango also it may have a direct relationship. So we are going to have this vectors pretty much similar. With respect to food, yes, apple belongs to a food item, right? So this will probably have a good value. It may be 0.91. This is also 0.92. Right? And similarly, I'll be having different vectors, right? So here, what we have done is that each and every vocabulary word is represented based on this feature representation, right? And here, the feature representation need not only be 300 dimensions. It can be 100 dimensions. It can be different dimensions, right? But here, I'm just showing an example with respect to Google. And what will be these features? That will also not be exactly known. But just consider that I'm just giving an intuitive example that yes, based on some relationship with respect to the word, you're able to get this specific vectors. Now there are a lot of advantages with respect to this, you know. Why I'm saying you? Because suppose let's say if I do a calculation which is like king minus man plus queen. If I do this calculation, and this is a famous calculation which is also written in Google research paper. If I probably do this calculation, the output that I'm going to get is something called as woman. Okay. I will definitely get it as woman. Why? Over here, woman is not there. It's okay. So let me just remove it. Suppose if I say king minus boy plus queen, then the output that I'm going to get, see, king is this vector, right? I'm subtracting with boy and then I'm adding it up queen. At the end of the day, you'll be seeing that the girl will be much more related to boy. So I'm going to get the output as girl. Here I'm just doing the vector calculation, and this is what kind of relations we'll be able to get it. You know, this is an amazing thing. We are getting this kind of relation just by seeing these vectors, which has been provided by Word2vec. Again, I'm not going to do the calculation here. I've just randomly stuffed some values. But in the real Word2vec use case, you'll be seeing that if you do this kind of calculation, you're going to get girl. And this I will show you practically also as we go ahead. Once we use this Google Word2vec, which is basically trained on 3 billion words, which is quite amazing, right? So let me give you another example. Let's say here what I'm doing, instead of using 300 dimension, I'll represent every word by 2 dimension. Let's say I have 0.95, 0.96. Man is represented by something like 0.95, 0.98. Let's represent like this. Okay, I'm just giving some values, okay, some meaningful values, so that you'll get an idea about it. Let's say queen is given as 0.96. Let's say, because this is the opposite of this, right? And again, this can be the similar keyword, similar vocabulary. And with respect to woman, let's say that I'm having something like 0.94 or 0.96, let's say. Then what I do is that if we do the calculation of king minus man plus queen, I'm going to get the woman, right, as the output. Now, what these vectors represent, that also you really need to understand. It is super, super important. And that is where I'm going to discuss about something called as cosine similarity. Okay. Cosine similarity, super important topic with respect to understanding these things, because if you understand these things and all. Now see, over here, king is given by two vectors, right? 0.95, 0.96. So obviously I can basically construct this into a 2-dimension. Let's say that I'm getting king over here. Okay. And in order to make you understand, let's say queen is over here. Okay. Or queen can come over anywhere. Let's say man is over here, right? Man is over here. If I probably say king with respect to gender, right, this two is going to be the most nearest word when compared to queen, right? So how do I calculate the distance between this vector and this vector, which is provided in this form? All I do is that I try to probably calculate the distance like this. Okay. I try to find out the angle. And for this, to find out the distance between two vectors, we use a distance formula, which says it is nothing but 1 minus cosine similarity. Now, what is cosine similarity? This is super important to understand. Cosine similarity, I can basically say that cosine similarity is nothing but the angle between these two vectors. Let's say the angle between these two vectors, let's say I'm just taking as an example, is 45 degree. Let's consider. Then this is nothing but cos 45. Cos 45 is nothing but 1 by root 2. And probably I think this is approximately equal to 0.7071. I've done the calculation. If it is wrong, just let me know. Okay. But over here, then the distance between these two vectors will be nothing but 1 minus 0.7071. Now, if I'm calculating the distance, it is 0.29, let's say. So if I'm getting this 0.29 distance, right, I will say that, okay, almost this particular word are similar. Let's say if I have two more vectors, if I have two different vectors, one of the vector is basically over here. One of the vector is over here. Then the angle between these two is nothing but 90 degree. In the case of 19 degree, my distance will be nothing but 1 minus cos theta. Cos theta is nothing but cos 90. Cos 90 is nothing but 0. 1 minus 0 is 1. So I can definitely say this vector and this vector are completely different because the distance between them is 1. If the distance is nearer to 0, I will say that they are almost similar vectors. Now in this case, it is 0.29. I can say that, okay, somewhat similar, right? Let's say if I have one more vector which is in this point only, then I can say that these two vectors are almost same because the angle between them is cos 0. Cos 0 is nothing but 1 minus 1, which is nothing but 0, right? Because over here, the angle between these 2 points is nothing but 0, right? There is no angle at all, right? So if there is no angle, then I will be able to find out the distance. In this case, my distance will be nothing but 1 minus cos 0. 1 minus cos 0 is nothing but 1 minus 1, which is nothing but 0. Now, if the distance is coming as 0, that basically means these two are same word, right? Now, so this is super important because recommendation also happens in this way itself. Now, in recommendation, let's say I have a movie which is like I have Avengers. Let's say Avengers is over here. Where do you think Iron Man will come? Iron Man will come again near this or near this at this particular point only, right? Iron Man will be coming and it will be based on different feature representation, right? Whether it is a comic movie, whether it is an action movie. So action, comic, right? Or comedy, these all are feature representation. Try to understand this. And movie name is basically my vector, my vocabulary. It can be Avengers, it can be this one, right? So I hope you're getting an idea about how Word2vec is basically working. At the end of the day, we are basically creating a feature representation of every word. Okay, and we are able to find it out. So yes, this was about Word2vec. Now what we are going to do is that you need to understand that how this feature representation is created and how this vectors is basically created. How this vectors, because here I have randomly written boy to gender is -1, boy to girl, girl to gender is +1, because I said that, okay, this may be the opposite one. Now you'll get an idea that how in an deep learning neural network, basically a simple neural network, how this entire Word2vec is trained. And that is what I'm going to discuss in my next video. Then I'm going to also show you the practical implementation. So I hope you're able to understand this with respect to this, a very good, amazing model developed by Google, a very good architecture with respect to this, and we'll try to solve that in the upcoming video. And I'll give you a clear idea about it. Okay. Just the prerequisite is that you really need to know about ANN, loss function optimizers and all. Hello guys, so we are going to continue a discussion with respect to Word2vec. Already we know Word2vec are basically of two types. One is CBOW, which we have already seen previously, continuous bag of words, and scriptgram. In this video, what we are going to do is that we are going to understand that how Word2vec model is basically created. What is the deep learning model that we are specifically saying, how the inputs and outputs are there and how the model is basically trained. One important thing is that you really need to have a prerequisite knowledge about ANN, loss function and optimizers. So if you do not have this, I would suggest, first of all, please make sure that you have some knowledge about this, right? Before you understand this. Now, with respect to Word2vec, one more important thing is that in Word2vec, we also have a pre-trained models, right? Now, if I talk about a pre-trained model like Google, right? Google has a pre-trained model with respect to Word2vec, which is trained on 3 billion words. And we can also train a model from scratch, okay? And again, the reason why I'm taking this, because you really need to understand that how that feature representation is basically getting created, okay? Now, let me go ahead and let me say is that, let me take a simple corpus and let's say that first of all we'll start with CBOW. Okay, so we are going to discuss about CBOW, which is nothing but continuous bag of words, and how this model is basically created. It is a type of Word2vec, right? Continuous bag of words. Now, to solve any problem, I will definitely have a data set. So let's say that this is my corpus. And remember, corpus, because all these models, like Word2vec is trained on a huge data set. Like this particular pre-trained model from Google is basically trained on 3 billion words. So let's say I have a corpus or a statement or a data set or a paragraph. It can be anything. And for just making you understand, I'm just going to take a simple paragraph. I'm going to say that, okay, iNeuron is iNeuron company, or iNeuron company is related to data science. Let's say I have this particular corpus. Now, remember, like this, in a use case, you will be having a bigger corpus. It can have millions of words, right? But let's say that I'm taking just a simple corpus over here, just a single liner. Now we're going to understand that how a CBOW Word2vec is basically created and how a model is basically trained with the help of deep learning. Now, first thing is that whenever we have a corpus, we really need to know what is our input data and what is our output data, because Word2vec altogether is a supervised machine learning, right? So first of all, what we do is that we select a window size. And I'll talk about this window size and why it is super important. Let's say that I'm going to select a window size of 5. Now, this window size is super important to basically create your input data and output data. Okay, super important. Like what should be your input data and what should be your output data, so that you can train your model, right? Now, this window size 5 indicates that how many words I need to select initially. So let's say I am selecting 5 words. So here is my 5 words. Now, from this particular 5 words, I will take the center word. Now understand how I will take up this window size 5 words and convert into input and output data. So let's say this is my input data and this is my output data. Okay. Now the central element that I've actually taken over here is right. Now in the input, I will be having iNeuron company, and then on the right hand side I have related and I have 2. Okay. Now why you may be thinking that I'm taking the forward and the backward, because understand, if I'm taking this as a central word and this will basically be my output word. Okay, this is basically my output word. Now it should be knowing that what all words are in the forward context and what all words are in the backward context. So that is the reason we are creating in this particular way, so that this is output should be knowing about its forward word and its backward word, just to get some idea about the context of that specific sentence. Now this is the first step. Now when I took the window size as 5, the initial 5 words, I divided my data set into input and output. Perfect. Now the next step is that I will go ahead and I'll move this window by 1 step and take the next 5 words. So the next 5 words over here is nothing but, so here this is my sentence 1. So sorry, input 1, And now this will become my input 2. And here I will be having company. Okay. And again, from all these 5 words, which is my center word. So this is basically my center word, related, right? So related. So here I'll write company is 2 and data. So this is my second input. And over here, the output will basically be related, right? Then similarly, I will go to the next step and I will push this windows to one step more. Okay. So here now I'll be having my third sentence with respect to my input and output. And the third sentence again, which is the central word. So this will basically be my central word. So here you have 2. Okay. And here I'm going to have is related. Okay. And then the right hand side, data and science. Now you may be thinking, Krish, should we only take the window size as 5? No, you can take any value. You can take any value. And why this window size is playing an important role, I'll just say in some time. You can take up any value, but don't take an even number. Take an odd number so that I will be getting the central element which I'm taking as an output will have the correct number of words in the forward context and in the backward context. Okay. So is related data science is there, right? Now, which is the central word over here? 2, right? So I'm just going to write it as 2. Now this became my input and output. Now what I'm actually going to do is that I'm going to train my model with this. Very simple, right? I'm going to train my model with this. Now how the training will basically happen and why do we say this as continuous bag of words, right? So that part also we'll try to understand. Okay. We'll try to understand in a better way. Now let's say that since we are discussing about continuous bag of words, let's say with respect to bag of words, suppose if I have this particular sentence, right? So let's consider that I have this many number of vocabulary only. So how many words I have over here? I'm having I neuron, okay, and probably I have company, okay, and I have related, and I have 2 word, okay. Now understand this, okay? This is super important to understand. You need to understand that how many vocabulary of words are there. So over here you have 1, 2, 3, 4, 5, 6, 7. So 7 total unique vocabulary is there. Now wherever I have I neuron, what I'm actually going to do is that I'm just going to make it as 1 over here initially, and there will be 6 zeros, so, right? 1, 2, 3, 4, 5, 6 zeros, right? So with respect to this entire vocabulary, wherever I have I neuron, that will be represented as 1, 0, 0, 0, 0, because remaining all the elements will be 0, right? And now when I go to company, what will happen? Then my second element will basically have 0, 0, 0, and all the elements will be 0. Similarly, if I have related, right? In related, which word will be 0? Which word will be 1? If I go ahead and write it 0, 0, 0, 1, 0, 0, right? And finally, you'll be able to see that the next word that I'm having is 2. So 2, with respect to 2, here you can see 0, 0, 0, 1, 0, 0, right? So all these words are there, right? And this is based on the vocabulary size, and this is what is my bag of word representation. This we have already learned it based on my vocabulary. What is my vocabulary? The first word is I neuron, then company, then related to data science, right? Something data science, right? So all these words are there. Now understand, this is what is my bag of word representation. So if I really want to represent this entire sentence, I basically need to convert this into this dimensions, right? I neuron will be given in this vector form, company will be given in this vector form, related will be given in this vector form, and 2 will be given in this vector form. Very simple, right? Every word is basically converted into a vector based on the vector size, right? Very much clear, very much simple. I hope you are able to understand this, right? So what I have actually done based on the vocabulary size, I have actually converted each and every word into vector. Wherever I neuron is there, I'll not say this as bag of words. I'll basically say this as one hot encoding, right? Now, one very important thing that you need to understand. Over here, you'll be seeing iNeuron company related to all these inputs and outputs. So I cannot probably send this text directly. I need to convert this into some vectors initially to send it in as an input to the neural network also. So for this, what I'm actually going to do, first of all, you know that how many number of words I have, how many number of words I have in the vocabulary. I have iNeuron, I have company, I have is related to data science, right? So they are around 1, 2, 3, 4, 5, 6, 7. Right? 7 words are there. Now, if I probably use one hot encoding technique, now see this. Okay, this is super important. In one hot encoding technique, if I probably consider iNeuron, let's consider the first sentence. Over here, I have iNeuron, and then I have company, then I have related, and then I have two, right? So for all these words, how I'll be giving the one hot encoding representation, wherever there will be iNeuron, I'm just going to make it as 1. Remaining all will be zeros. So there will be around 1, 2, 3, 4, 5, 6 zeros. Similarly, when company is there, I'll make this as 1 and remaining all will be zeros, right? Similarly, related is in the 4th word. So I'm going to make it as 0, 0, 1, 0, 0, 0, and then 2 is present after this. So I'm basically going to write it as 0, 1, 0, 0, right? So this is pretty much clear till here, right? So here you can see that I've basically done this a simple one hot encoded format. That basically means if I really want to pass iNeuron, I need to give this as my vector. This is what is the understanding. And this vector is basically given by 7 dimensions. So 7 vectors I'm giving it over here, right? 1, 0, 0, 0, 0. If I'm sending company as my next word, then this should be the vector it should go, right? Then if I'm sending related, this should be the vector I should go. So similarly, all these particular words will be converted into this particular vector using one hot encoding. Now let's go to the next step, which is super important. Okay, super important. What does CBOW basically mean? Continuous bag of words. Okay. This is nothing but this is a fully connected neural network. Now you will be able to understand how these models are created. Fully connected neural network. Okay. Now in this fully connected neural network, you will be able to see one very important thing. One is, first of all, just understand how many number of input should I be giving, right? Like how many words I will be giving as my input, right? Since my window size is same, window size is 5, all my inputs are fixed. I hope that is very much clear, right? Now in this particular problem statement, you'll be seeing I'm giving 4 words in every sentence. So my input is basically fixed. Now iNeuron, when I give my word iNeuron, let's say in the first case, I give my sentence 1 and this is my sentence 1. When I give iNeuron is represented by 7 vectors over here. It is represented by this vector. Then company is basically represented by this vector. So if I probably see in fully connected layer, my first input layer will basically be nothing but, so here you will be able to see, this will be my input. Okay. And this is super important, guys. See this. So this will be my input, my first input word. Okay. And understand I'm creating this circle as my inputs. Okay, I'm just creating this circle as my input. So if you see 1, 2, 3, 4, 5, 6, 7. 7 inputs I'm giving it, right? Now when I give this 7 inputs, then similarly, how many words will be going? 4 words will be going, right? So 1 word, 2 word. So this is basically my input layer. So this layer is nothing but my input layer in a fully connected layer. A simple ANN, if I probably consider an example of ANN. So here also how many inputs I'll be having? 1, 2, 3, 4, 5, 6, 7, right? And this is my first word, second word, third word, fourth word. So I will be having 4 different words over here that will be going. And each word will be having a dimension of 7 vectors. 1, 2, 3, 4, 5, 6, 7, right? I'm not giving this value. Don't consider that these all are zeros. Okay. I'm just saying that these are my input layer, input circles. Okay. That is how we create it in ANN, right? And then probably I have my last one. So this is my input, right? I'm basically designing the neural network, how it will look like when we are training a Word2vec. So these are my four words. Understand, in the first case, I'm going to pass iNeuron over here. So let's say I'm going to pass over here iNeuron. This will be my input over here. This is represented, iNeuron will be represented by 1, 0, 0, 0, 0, 0, right? And similarly, if I go to the second word, that is like company, then it will be represented by another word like this, right? It will be represented by a different vector like 0, 1, 0, 0, 0, 0, 0, right? 7, it will be 1, 2, 3, 4, 5, 6, 7, right? Now, similarly, other words will be represented like this, okay? So this becomes my input layer, okay? And every input is basically given by a vector of 7 dimensions. So because I'm representing every word based on the vocabulary size using one hot encoded. Now this becomes my input layer. Now let's go to the middle layer, that is called as the hidden layer. Now in this hidden layer, this is super important. Just pause the video and guess what will be the size. You know our window size is how much? Our window size is basically 5, right? So I'm just going to make this as my window size. Okay. So this is my window size. Now in my window size, if you remember, how many we are having in our window size? Our window size is nothing but 5. So I will be having 1, 2, 3, 4, 5, right? Window size is basically 5. So in my hidden layer, I'll be having this 5 vectors. Okay. So just understand that with respect to this 5, our window size will be set over here. Okay. Now with respect to the output, in output, how many values I have? I just have one value, and each word, I just have one word in the output, right? And each word is represented by a vector of 7. Because if I am also considering this is using one hot encoded, I'm going to get this vectors of this dimension, that is 7, right? So what I will be doing in output, I will basically be having another output layer like this, which will again be having 7 different outputs. 1, 2, 3, 4, 5, 6, 7. Okay. Now this is how my fully connected neural network will look like. Now you need to understand one thing. Over here, each and every node will be connected to the other node, right? Like this. Like this, it will be connected. Like how an ANN will work. It will be connected like this only, right? Similarly, right? Now, similarly, these all will be connected to this also. So in short, I can basically make a very simple connection like this, which will look like this itself. And this will be entirely connected to this, right? Understand all these lines will have some initialized weights, and we need to train these weights. And this is what it happens in ANN, right? Similarly, this will be connected to this. This will be connected to this. This will be connected to this, right? And finally, this will also be connected to this, right? So everything is basically getting connected. And from the hidden layer, this is my hidden layer 1, HL1, and this is my output layer, right? Now from this hidden layer, it will basically get connected over here, and this will get connected over here. Okay. Now understand one very, very important thing. Okay. This is super, super important. Fine, we are connecting it with the help of loss function. We'll also do forward and backward propagation. Now let's say we'll consider, let's pass this particular word, iNeuron company related to. So I have passed iNeuron company, and here also you'll be able to see I'm passing related to. Very simple. Okay. Let me just zoom out a bit. Okay. Now once I pass all these things, what happens over here? With respect to this 7 output, I already know what is my real output is, right? I'll be getting some values over here. Okay, I'll be getting some values. Okay, but the real output is what? If I consider is my third word. So is my real output. So this will basically be represented in this vector format, that is 0, 0, 1, 0, 0, 0, 0, right? But after training, while we are training the model with different weights, this is my true output. This is my Y. I may also get different Y hat, right? I may get some values like 0.25. I may get some values like 0.33. Then like the 0, 1, 0, 0, 0, something like this. Then what we do? We basically calculate the loss function, and based on this loss, we need to reduce this. We do the backward propagation, right? Backward propagation. And we do it unless and until the difference between Y and Y hat are minimal. Okay. And this process is continuous. Very simple. But now you really need to understand one very important thing. Very, very important thing. Now, since this is giving me a specific output. Okay. This is basically giving me a specific output. When I say my middle layer is basically window size of 5. Window size of 5. That basically means over here in the Word2vec, when I said I will be getting a 300 dimensions over here, when I'm using Google Word2vec, This is all because of this window size. Okay. That basically means if my window size is 5, I'm going to get the output as 5 for every word. That basically means when a word is getting converted into a vector, I am going to get a size of 5 vectors. And this will basically be my final output. Now I hope you are able to understand. Again, let me repeat it. The reason I have actually selected window size is equal to 5 because I want to probably provide a feature representation with a vector size of 5. Okay, that basically means every word will be converted into a 5 vector. Now, when I took an example of Google, which was getting converted into 300 dimension, that basically means my window size is 300. And more the bigger window size, the better the model can basically perform. Okay. So in this case, you'll be able to see that over here, my window size is 5. That basically means if I see from starting, right, my metrics for every word will be 7 cross 5. That many number of weights will be there. Then here also I'll be having 7 cross 5 weights. Here also I'll be having 7 cross 5 weights because I'm giving 7 different vectors. Here also I'm having 7 cross 5. But in this case, I will basically be having 5 cross 7. Now, what does 5 cross 7 basically mean? When this loss gets reduced, then my final vector will look something like this. This all will get connected to this. This all will get connected to this. Let's say it is getting connected to this one. It is getting connected to this one. It is getting connected to this one. So once we have this particular connection, let's say our first word over here is, what is our first word? If you probably see, what is our first word with respect to this particular vectors with vocabulary? You'll be seeing iNeuron, right? This is my vocabulary. The first word that is basically getting represented over here is iNeuron, right? So iNeuron will have an output dimension of 5 vectors because I'm getting this 5 vectors over here joined to this. So this 5 vectors will be like 0.92, it can be 0.94. Based on the training, it can be 0.25, it can be 0.36, and it can be 0.45. And this is based on some feature representation. So I hope you are able to understand. And this is how iNeuron will be represented. The second word that we have in the vocabulary, that is company, right? This will again get connected to this company. This will also get connected. This will also get connected. This will also get connected. This will also get, and this entire word will be the vector for the company itself. And for the company, we may have a different vector, but again, the size will be 5 dimension because our window size is 5. And this training of forward and the backward propagation, when the loss is minimal, then only we'll be able to get the vectors. And that vector is basically taken and it will be represented in the format of the feature representation for each and every word. So I hope you are able to understand like how Word2vec actually works with respect to CBOW, right? That is continuous bag of words.